Well, hello, physics fans. We're going to start on Chapter 3 right now, the Introduction to Projectiles. This is assuming that you've done constant velocity, which was Chapter 1, and accelerated velocity, constant acceleration, which was Chapter 2. So here we go. Let's begin with Chapter 3, Projectiles. So you should have this package. If you don't, I'll see if I can put a link to downloading it in the section below. Projectile motion. Any rock, any boulder, any object that is projected by some method then continues moving along because of its inertia is a projectile. A baseball thrown in air is an example of this projectile. So read that through. Few things that we should know in physics. A projectile is an object that has only gravity pulling down on it. Gravity being a force causes the object to accelerate downwards. The force of gravity could never alter the horizontal velocity, and that's a big idea here. The big idea for physics, and once we go into 2 dimensions, which this chapter is beginning, is that the forces in one dimension cannot, or the pushes or the gravity in one dimension cannot cause the object to accelerate in another dimension. So gravity is vertical, it will not affect the horizontal motion. The results of the vertical force acting upon the horizontally moving object will cause it to deviate from its linear path. So something that's moving horizontally, and you put gravity on it, it'll start deviating from its linear path. When a projectile is fired, its path is to be parabolic, or it's the shape of it is a parabola. And that's kind of like the 2 words, parabola and parabolic, is kind of like circular and circle. And number 5, here it is. When we start analyzing, that's what we're doing in physics. We have a few ideas here with that mentioned above. When analyzing the motion of a projectile, the velocity always resolved into horizontal and vertical components. So we set up a horizontal table and a vertical table to contain our data. And vertically, the acceleration is 9.8. We'll do that in physics 11 here. And that's gravity is down at 9.8. And then because there is an acceleration, it's chapter 2, we deal with the vertical numbers with the 4 kinematic formulas. What are the 4 kinematic formulas? In case you don't have them, this is a good time to write them down. In case you don't have your formula sheet, Vf squared equals Vi squared plus 2AD. D equals VIT plus 1/2 AT squared. D is also equal to VI plus VF all over 2 times the time. And this one, the last one, is the definition of acceleration. Acceleration is the change in velocity over time, which can be better written as Vf minus Vi all over t. And the best way to rearrange it is Vf equals Vi plus At. That's the same formula written several different ways. Okay, those are the 4 formulas that you use when solving the vertical components. And horizontally, we only use this formula. Why? Because horizontally there's no acceleration, that means constant velocity, and that's the only formula we have. So we can also rewrite that as D, oh goodness, my screen keeps moving. D equals velocity times time. So just organize it into the 2 dimensions. So I'm going to scroll through the next page so that you can, and it tells you how to fill things in. Here it is. Here's an example question. A stunt car drives off a cliff horizontal, velocity of 20 meters per second, and the cliff is 44.1 meters in height. Fill in the values that we know. Okay? It's telling you to look at this and going, okay, there's a vertical acceleration that's down. There's a vertical distance that's 44.1 meters down. And then there's a horizontal velocity of 20. So put those into their table. Okay? 9.8. I'm going to skip the units and put down. And the distance is 44.1 meters, and that is down. And horizontally, it's 20 meters per second. Why don't I put a direction in there? Why do I put units? Well, I don't need to put the units. I don't need to put the direction. It's not going to change. What isn't obvious is that it said we can actually take a fourth piece of data out of this, and it's that the initial vertical velocity is 0, because it says it's fired horizontally. So it's launched off of a cliff. Let's just kind of picture this. It's launched off of a cliff, and it lands like that. Okay, but when it's launched horizontally, it's going this way. So it's not going up or down the moment it leaves the cliff, it's going that way. So the initial velocity is 0. Okay, skipping on down. Whoops, too fast. Vertically, we have 3 of the givens. Once we have 3, we can calculate the other 2. So let's just solve for VF here. And we'll use this formula because it doesn't have T in it, and we don't have T. So VI is 0 plus 2 times 9.8 times 44.1. So VF squared is going to equal, pull up my calculator, 2 times 9.8 times 44.1, and that's 864.36. I'll just put that all down for now. 864.36, and then I'm going to square root it to get VF, and VF is going to equal 29.4. Now mathematically it's plus or minus, but we know it's going to go down. So we already know that the negative of going up, the opposite direction of that, is not going to happen. 29.4 is the answer that we have, and it's down. And now we solve for T. And this is the formula, and rearranging it for T and everything like that, we get T equals, and it'll be VF minus VI, but VI is 0. Right? So then T is just going to be VF, which is 29.4 divided by the acceleration 9.8, and we get 3. That's exactly 3. Okay, if you didn't follow the formula there, let's just do that. VF minus VI all over T, but this is 0 because the initial velocity is 0 there vertically. And then rearranging it, we just crisscross it and we get that one. So this answer is 3 seconds. And so we drag that 3 over to because the time in here has to be the exact same time in here, because it's analyzing just one motion, but we're looking at it in 2 different ways. The time can't change in how we're looking at it. And now we just solve for the distance, and that's what I have written down here below. Distance is velocity times time, only when there's 0 acceleration. That's what it is with horizontal. So the velocity is 20, and the time is 3, so the distance is 60. So let's just recap what we've learned, and where does it all plug in? A car flies off, this is the original question, 44.1 meter high cliff, and it takes 3 seconds to land. Meanwhile, during those 3 seconds, the car moves horizontally 60 meters to the right. So as it plummets and follows this projectile path, which is called a parabola, so a parabolic path, it falls vertically 44, it travels horizontally 60. It lands at this location, still with this speed horizontally, but now it has this speed vertically. Okay? So, let's try to solve this question. Okay, so right now, if you're working on it, how about you pause it? Try it out. Now that you're coming back, welcome back. A stunt car drives 10 meters per second horizontally and lands 40 meters from the base of the cliff. These things are plugged in. You only have 2 things here because it's going down, and because it's launched horizontally, that's why this is 0. But we have 3 unknowns here. We can't solve it. Every one of those formulas have to have 3 inputs to get the 4th. So we solve for time, this one, and t is d over v. T is going to be 40 over 10, which is 4 seconds. My hint in square brackets is the answer, 4. Now we copy that 4 over to here. We now have 3 items in here. We can solve for the other 2. Okay, so solve for VF and then D. So VF without D will be VF is VI plus AT, which is going to be VI, which is 0, plus A, 9.8 times 4. And that will be 39.2 meters per second. And that'll be down. And then we solve for the distance, and the distance without VF will be D equals VI T plus 1/2 AT squared. And this is 0 because VI is 0. So it's just going to equal 1/2 9.8 times 4 squared. And 4 squared is 16 times 1/2 is 8. 8 times 9.8 is 78.4 meters. Okay, so hopefully you got those and it confirmed it here. And there was a visualization of my answer. Whoops. Stays at 10 meters per second horizontally. That's important to know. It's always traveling horizontally. And vertically, every second, it increases its speed. It goes from 0 to 9.8, and to 19.6, 2 times 9.8, and 3 times 9.8, and then 4 times 9.8. Every second, it's increasing by 9.8. That's what gravity is. We've studied that in falling. Okay. Here's a good, tough question. Good concept question. If the cliff was infinitely high and the car kept on falling, would the path of the car ever be pointing straight down? So like after a day, not just a minute or 2 or 3 or 4, but a day or a week of falling, that's a long time it's going to be accelerating down. Would ever the path, the direction, be straight down? Would it ever go straight down? Answer in the next video.